Hi everybody, welcome to my 12th axial bar video. In this video I'm going to be solving this problem here for the internal forces in these two rods. If you want to know something else about axial bars, feel free to check out any of my other axial bar videos. Okay, so if you recall, the way to solve something that's statistically indeterminate. Wait, how do I know that this is statistically indeterminate? Alright, well let's just take a general overview, alright? I could just tell you it's statistically indeterminate, but it's always good to prove it. So there's going to be a force in here, NB, and a force in here, NC. We're also going to have a reaction into support. So the moment equation will give you N1, N2. The reaction is not included in the moment because it's at a distance, no distance, so it's no contribution on the part of the moment. We'll also do forces, but when we do forces, we need to include this. So we'll have two equations, one force equation, one moment equation, and we won't know N1, N2, and NB, NC, and the reaction. So not enough information. Alright, so that's why this particular problem is statistically indeterminate. So let's get ahead to solving it. So in order to find NB, we need to expose NB, so we make a cut. Same thing with C. And now looking down, draw a free body diagram of this piece. Okay, so we have a load P still being applied here. Alright, we'll just refer to that diagram for the dimensions. I'm not going to draw them in. And then here we're going to have NB, and here, and C. Alright, and then a reaction. Suppose we could include it even though it's not important. Alright, now for moments, I like to say that counterclockwise is positive. Alright, always good to define your directions. So that means NB times the distance it acts, 2b, plus NC times the distance it acts, that's 4b, minus P times 5b equals 0. Alright, so sum of the moments about point A must equal 0 for equilibrium. Alright, as you can see, we can factor out a b, and because it's 0 here, the b goes away. So let's write this equation as simply this: 2NB plus 4NC equals to 5p. There you have it. Our equilibrium equation. Alright, so let me just write that in here. Equilibrium. Alright, now we need to move into displacement, the geometry of displacement. Alright, we need to find a relationship of the displacements of this point and this point so that we can express them in terms of NL over EA, therefore allowing us to solve this. Alright, so whenever you need to find the geometry of displacement, I always find it really useful to draw the clearest picture you possibly can. So I like to draw my bar in its original position, and then in its final position I'll draw it in terms of like a dotted line. So what's going to happen when we pull down? Well, it's just going to kind of angle. Of course, at that point we're going to remain fixed. Alright, now it's got some sort of hinge there. Okay, so it can't provide any resistive moment. So the displacement is going to approximately look like this here. Alright, and now technically this would have to be a 90-degree going this way, but let's just assume the displacement is so small that this is 90 degrees. That makes it handy for us. Alright, so the displacement of B is going to be this distance here. Alright, delta B. And then conversely C is going to be here. Alright, now this distance is helpful to draw in to B. Now, using similar triangles, we can find a relationship between this and this. Alright, so since this is all part of the same triangle, that's what similar triangles mean, that means the ratio of any property of that triangle is going to be the same. Alright, So let's just say the ratio of this side length to this side length would be the same as the ratio of the full side length to this. Alright, so using that idea, delta B over 2B is equal to, by the properties of similar triangles, delta C over this distance here, 4B. Alright, so rewriting that, we can say delta B is equal to delta C by 2. Alright, there we go. Equilibrium, displacement relationship. And now we're going to move into the displacement force. That's what I like to call it. Relationship. That's basically using this equation and plugging that back into here. Alright, and then I'm going to do that straight away. And delta B, the displacement of B, is due to the properties of B. Alright, so it's just going to be NB, LB, for EB, AB is equal to, same thing here, but now it's divided by 2. 2. Okay, now we've been given a few of these values. Alright, we know the area of the B and C. We're told that E is 140, so I mean the E is the same for each of these. It's made out of the same material. I'm told that they're both of a length L, and we don't need to know that length because, as you can see here, if LB equals to LC, this goes away. Alright. Same thing with E actually. Alright, if the E is the same, E doesn't matter. Alright, so that bit of information is actually kind of useless. Alright, EB, EC are the same, so you can cancel them out. Therefore, we can write NC is equal to 2 NB times the ratio of the areas, AC over AB. There we go. Now we have all the information we need. We have NB, NC, one equation, NB, NC, another equation. Two equations, two unknowns. Alright, so let me just name these equations to make it straightforward as we're doing the algebra. Alright, so the first step is going to put 3 into 1. Okay, grab another piece of paper here. So putting 3 into 1, we get 2 NB plus 4. Alright, that was this equation here. And then NC, well, we have that right here. So we basically put this piece of the equation right into here. Okay, that's 2 NB, the ratio of the areas, equals 5P. Now we can solve for NB. Let's just do one more step first. ANB, alright, because that just multiplies out. Now AC over AB, we just need to know the ratio. Alright, now we're told that AC is 150 and AB is 75. That means that AC is twice as big as that one. So we don't need to go through and put those numbers in. We just know that it's twice as big, so we can write it. And this, of course, is just equal to 2. Alright, and working through a little more algebra, you can find NB is 5P over 18. Alright, then we're going. Now that we know that NB is, we take NB, plug it back into equation 1, and then just solve for NC. Alright, let's just go through that. We're going to put that in this equation here. 2 times NB plus 4NC equals to 5P. Alright, a little bit of algebra. We can find NC is equal to 10P over 9. Alright, so it appears that C is taking a way bigger component of the load than B. Alright, and that intuitively makes sense because it's further this way, so in terms of the moment it's going to be taking a lot more. All right, and we also have the difference in the areas, right? So even though this one's twice as big, it still is a lot bigger in terms of the force. Okay, so I've just solved for the internal normal forces. That's the bulk of this problem. Now, if you get this question in class, they'll probably say, find the maximum force P if the stress allowable is, I don't know, some value. Then you're just going to find the stress by taking the normal force divided by the area and then solve for P. All right, now you need to check each bar because the one might reach the stress before the other one. All right, so it's good just to check every single situation. Then they can give you some other question. They might ask you to find the displacement. All right, so I'm not going to get into that, but since we know the internal forces, all right, and C and B, we could just go back to this equation right here. All right, right here. So we know that delta C is just this. So we know NC now, we plug it in, you can just solve for it. All right, pretty straightforward. Okay, so that's pretty well it for this example. So let's quickly sum up. We realized it was statistically indeterminate. We didn't have enough equations of equilibrium to solve. So we did our best. We made our equilibrium equation, taking the moments. We found a displacement relationship. We're drawing a clear picture of what it is before and what it does after, and finding the relationship in between. Then we went to a displacement force relationship, plugged in all the values for each displacement, and then took the resulting answer and plugged it back into our forces equation. And then boom, we solved for NB and NC. Alright, hope this helped, and I will see you in my next axial bar video.